Okay, so first exercise, this is from last year's exam actually. First question, so we'll do that. We have basic line formation and line broadening, so that gives you some pointers toward what we're going to do here. We're going to approximate the general astrophysical gas cloud as a homogeneous plane parallel slab in LTE and of constant temperature T. Already that should give you some associations what we're dealing with here, right? Homogeneous slab, we know the radiative transfer solution through a homogeneous slab is sort of a core result that we have derived, and that, well, we will work with here. LTE, a constant temperature C, that means that it's going to have a constant temperature T, it's going to have a constant temperature rho, and that means that the opacities and emissivities are going to be constant throughout this, which is, of course, why we can say it's a homogeneous slab. Incident radiation, I0 entering from below, or we can put it from the left, which you may take to be the same within the line and the nearby continuum, C. When viewing the slide from above, what will you observe? And in the first year, we're going to neglect the extinction in the continuum such that the line opacity or extinction is greater than the continuum, which we can approximate to 0. We neglect it. And thereby, the optical depth, obviously, in the line is going to be greater than the optical depth in the continuum. It's important here that we're going to set that to identically 0. And then we have that the line is still optically thin, but it's not identically to 0. We're going to solve the appropriate transfer equation and show under which conditions you observe emission lines and absorption lines superimposed by the nearby continuum. And we're going to discuss astrophysical examples. Then in the B, we're going to do optically thick case, okay? And C. And in the third, we're going to consider the line broadening, the full width half maximum of the Doppler, the natural, and see where they become equal. All right, so let us start with this then. Should work. I'll bring my coffee. So, what do we need to do here? We have our homogeneous slab. We're viewing from above. We're saying now we have some radiation I nu 0 entering from below. It's going through here. And we're interested in what do we see? Okay? The first thing is, okay, this was of a constant temperature T, constant rho. It was an LT, so it's in T. Homogeneous slab, okay? So here I'm actually just going to write down the homogeneous slab solution, okay? If you want, you can derive it, but that derivation is for you in the lecture notes, huh? So the homogeneous slab solution is that the emergent, call it there at the frequency nu, it's going to be the incoming, right, at the bottom, e to the minus optical depth plus the source function 1 minus e to the minus tau nu. All right. Well, we already have a few, so that I nu in is I0. And that was the same in the continuum and the line, we said. We also said that this was a homogeneous slab in LTE, which is important because then we know that S nu is just our Planck function. Yeah? Remember the thermal versus scattering processes that we have discussed. And then in the first case, we had two processes, line and continuum, and we said that the continuum opacity, or extinction, alpha, could be set to identically 0, okay? So that means then that tau nu in the continuum, which is just then the integral of this over the length of the slab, so in dl, from 0 to L, if we put 0 there, and if this, I call it L, you can call it C if you want, it doesn't really matter, right? But this is just going to be 0. That's essentially the assumption that we had. Now, we had that the line, optical depth in the line, yeah, that was not 0. It was going to be this alpha nu line. Technically, this is alpha nu line plus alpha nu continuum, right? Because you have to add the opacities in the line. But this we have set to 0, and we have said that this is a homogeneous slab, so this is not dependent on position. So this is just going to be alpha nu line times the slab length, okay? Now, for that optical depth, of course, we know what the alpha nu line is. We can actually even put down so I'm going to do an extra step here now. You can analyze this without this step, actually, but, you know, because we have it, this is just a classical cross-section, right? The oscillator strength of the line times the number density of the transition, which we haven't specified now, so I'm just going to call it with the occupation number n, and the line profile function, phi nu, okay? And here I then neglected stimulated emission. If we want to include stimulated emission, we have this factor here, since it's LTE. All of this we know. Okay, so now we have tau line, we have tau nu continuum. Tau nu continuum is 0, so the solution for the nearby continuum, not within the line, is really trivial, right? This is identically 0, this is identically 0, then this is just I nu in, which is what we called I0, right? Now, for the line, we have that it is I0, the same intensity. The incoming intensity doesn't vary much across the line. And then we had the condition in number 8 that it was optically thin, but not identical to 0. So we had this condition. And here, of course, we have to do our Taylor expansion. This is the one that we know. E to the minus tau nu is approximately 1 minus tau nu for this condition. So this is just 1 minus tau nu plus the source function b nu of t. And if I insert this there, then tau nu, and this is line now, comes out. Okay. We can choose to perhaps rewrite this as I0 plus tau nu line, b nu as a function of whatever temperature we have, minus that I0, right? Okay. But we know that I0 is the intensity that it were in the continuum, right? That was the condition. So if we just divide by that, we get like a profile function within the line. I nu line divided by I nu continuum is just going to be 1 plus tau nu line, and then we have b nu of t divided by I nu continuum, or I0, depending on how we want to call it, minus 1. Okay. And here we have our profile function. So, what can we do with this? Well, we can just look at the expression, right, and see the question was, when do we observe emission lines and when do we observe absorption lines? Well, you can see that in this case, since we're in LTE, we can never get dominated by a stimulated emission in this case. Yeah? So this is always positive. So this one will always be positive, right? Yeah? That we can agree on. And then we have the condition that if this factor here is greater than 1, That is that if B nu of T is greater than I0, then P nu is greater than 1. And this is what we mean with an emission line. You can see that in this case, this emission line will follow the spectral shape of the line profile function, which perhaps is a Gaussian if we have Doppler broadening. Yeah? So then it will look something like this, where this level that I write here is the continuum level I0. And then as we go up, and then we'll reach a peak at the maximum at line center, as we know, and then it will go down again. And we have our emission line. If this condition is true. So, on the other hand, if B nu, the Planck function of T, is lower than, then we see that P nu, the profile function, is smaller than unity. So if we then draw the same here with some continuum level I nu in there, it will look something like this if we have the same profile function, where again this is nu equals to nu 0, this is nu equals to nu 0. Then we have an absorption line, right? Because if this is true, this factor will be negative, meaning that we have to subtract something from unity. If we subtract something from unity, we have a value that is lower than unity. So P nu is going to be less than 1. Right? We have an absorption line. Okay, so we can now discuss a little bit when this might happen. Well, if we assume now that the background intensity, I0 in this, also follows a black body of a different temperature, right? If I0 is also a black body, so B nu of T incoming, yeah? And this now has the T of the slab. Then we can directly see, since the over a line profile, the Planck function doesn't vary much. You know, you remember the broad versus the very sharp dependence of the lines. Then we can directly see that the condition here for getting an emission line is that T slab is greater than the illuminating temperature. Vice versa, that will give you an emission line. Vice versa, if T slab is lower than the temperature of the incoming radiation field, then we get an absorption line. Assuming the illuminating intensity of this cloud here, if we view near now, we're illuminating the cloud with some sort of temperature in, and then we have a temperature in the slab here. Yeah? And then we get these two conditions. Now, where do we have this? Well, the first is typical for our nebula that we have talked about, right? Because in a nebula, it can sometimes be, and we did this example in one, that we said that it wasn't illuminated at all. Now, what does that correspond to? Well, in this case, it will correspond to an illuminating temperature that is 0, right? Or an illuminating intensity that is 0. And then, of course, the T slab is always going to be higher than the illumination. So then you're going to see emission lines. And indeed, you see emission lines from some astrophysical nebula, H2 regions, etc., like we discussed. Here, we can sort of say, think about this in the very simple explanation. It's not fully sufficient, but of a star. If you think about the star, that you have like a slab, which is your atmosphere of a certain temperature, and you have the underlying star, which is the interior, right? Now, the interior we know has a much higher temperature than the atmosphere, okay? And therefore, since the incoming, the illumination from beneath in the star of this thin atmosphere here, which is actually then emitting the light to us here, since the T in here is going to be higher than the T in this layer here in the atmosphere, yeah, where T in is higher than the atmosphere, yeah, then you get absorption line, and that's normally what we observe from a lot of stars. We have seen some examples during the course. Okay, so those are two. Now, this, of course, is not a fully sufficient, but it's actually what causes absorption lines also in stars, because in practice, it's not like you have the interior and then an isothermal constant temperature atmosphere. But you know you have a temperature gradient, and since the opacities in the lines are higher than the opacities in the continuum is formed in slightly deeper layers in the star. And slightly deeper layers means slightly higher temperatures, meaning higher source functions. And therefore, the source function in the line is a little bit lower, and there go. However, there, of course, it has to do with the it's not a homogeneous slab, technically. Let's just say it like that. All right. And that was actually the discussion we needed for A. Okay? B. The case of optically thick. So that now we have that tau nu line is much, much greater than 1, but also tau line in the continuum is much, much greater than 1. What will you see then? Well, we have to go back then and look at our original homogeneous slab equation, okay? And if you were to get this question on the exam, you have to organize your paper better than I organized my blackboard here, huh? But I think that goes by saying. It's a little bit difficult when I can't move around. What was I doing? Yes, optically thick. Well, we know that we don't want to be up against the exponentials. Optically thick, we can neglect this, and we can neglect this. And it's just going to be the source function, which we know is the Planck function, right? So for the continuum, for the line, the I nu emergent is going to be B nu of T slab. Yeah. However, for the continuum, it's also going to be B nu T slab. So in this situation, if you have a homogeneous slab, and they're optically thick both in the continuum and in the line, you don't see it. You don't see the line because it's homogeneous slab. The only thing you see is a black body spectrum. So if you zoom in on the little region around the line, you will just see a continuum, a flat. Now you zoom out. Remember we had this zoomed in picture on the spectral line, and we zoomed in on the broad band spectral energy distribution. Then you will see a black body with the shape of a black body and with the temperature of your gas cloud. But you won't see any lines, which you can see directly from this solution here. Okay. Questions so far? We have any questions on Zoom? Huh? Why is this not? I want to go back to the meeting here. Nope. Nothing there. Just jump in if you have questions, okay? When you have them. Yes, please. Graphically, the question is, what is the line and what is the continuum? Graphically. I can draw it here. You have some images of this also in the lecture notes, but if you think about it, let's assume we have something that behaves roughly as a black body, and you think about the broad intensity output, yeah, as a function of, say, lambda. It will go something like this, right? Okay? But then imagine you have a spectral line, just one in here. Then that will be perhaps here, I don't know, in some shape of the spectrum, but it will be very narrow as compared to the extent of the broadband spectral energy distribution that we have over multiple wavelengths. So it will be something like this, okay? That's the spectral line, this is the continuum. So now if we were to actually, this is highly exaggerated, because if we were to zoom in on this little square here now, and just focus our telescope on that little delta lambda here, then actually it would look something like this. That is, this variation that we see here is actually so, it happens on wavelengths that are much, much larger than the delta lambda of a spectral line. So when we zoom in on this, you have a continuum here, which is flat, and then you have a spectral line there, okay? And the tilt here, well, sometimes, often, it can be tricky to what we call normalize spectra from astrophysical objects, but that's sort of something that you hopefully will learn in observational techniques or something like that. But technically, that's what we mean. So this would be then the continua, and this would be the line in normalized spectra. This is how it actually looks then when you take it from the telescope. If you could have an instrument that could take this whole bandwidth here, which often you don't, so you perhaps get something like this from your observational telescope. Yeah. So that's what we mean with the line and with the nearby continua. All right. More questions on this? Okay. Shall we do next C then? Okay. Yeah. Let's let us now consider the hydrogen Lyman alpha spectral line and assume the above astrophysical gas cloud is a neutral pure hydrogen interstellar gas, T 200 Kelvin. That's cooler than we normally do. Compute the full width half maximum under the assumptions that the line is exclusively broadened by one Doppler broadening, 2 natural broadening. You may assume a 2-level atom for the Lyman alpha hydrogen. Use atomic data as given in the lecture notes. Okay, that was nice. 3, if both of these broadening mechanisms contribute, estimate at which frequency displacements from line center their contributions become equal. Okay, so this we have all done. But, yeah, we have to interpret. So what do we want to do? We want to compute full width half maximum first. Okay, so let's focus on that. Doppler and natural. Doppler broadening first. I'm going to take this off away then. Yes. Doppler. So, just for the fun of it, so that we learn, I'm going to write the Doppler profile now. Phi x of x dx in this form. We have learned both, of course. Okay? Where x is nu minus nu 0, delta nu Doppler. Delta nu Doppler is the thermal nu 0 divided by c, and our thermal speed is square root 2 kT divided by m, where we have that T is 200 Kelvin, we have that m is the hydrogen atom, so the mass of the hydrogen atom. Okay, there's our nice setup for this. And then we're interested in the full width half maximum. So we remember, how did we do this? Well, first we took up the peak value. That's the maximum, right? That we know is at nu equals to nu 0, equivalent to x equals to 0. And in x space, it is 1 over square root of pi, okay? We want half that, right? And we're interested where we are in half that. So that means that e to the minus x squared divided by square root of pi is 1 over 2 square root of pi half. So we can solve this, of course, for x, which gives minus x squared, right, equals to ln of 1/2, or x equals to square root of ln of 2. Okay? That was half. So now we have computed half width of half maximum in x space, which I did so, like so. Okay? So this is half width of half maximum. So this one. But we wanted the full width, so we want to multiply this by 2 because it's symmetric, right? So the full width of half maximum for the Doppler line is 2 ln 2 in x space. So, of course, then, if we want this in a frequency space, which is normally what we want to do, right? Then our delta nu for the full width half maximum of our Doppler line is just going to be delta nu d times 2 times square root of ln 2. Okay. Now we have to calculate that. So first we need to calculate delta Doppler d by just plugging in these two values, keeping track of our units. We look up the hydrogen mass in our lecture notes. We have our cloud that is 200 Kelvin. From that we will get a V thermal that is, I did this, I think, or we can do it here as well, but yeah. We can do it here. You have your calculator. I can do it here, which is gonna be V thermal, right? What did I say? Square root of 2 times, and then I luckily have my library of constants and CGS mass hydrogen. So this is this, and if I divide it by 1e5, 1.8 kilometers per second. Okay. So this is 1.8 kilometers per second. Yeah. You plug that in now. Nu 0 divided by c. Then we of course have to know which line are we doing. We will use this relation because I know the values better in that. So that would be V thermal, nu that, divided by lambda 0. And lambda 0 for the hydrogen alpha line is 1216 angstrom, right? Remember to convert this to your CDS. Remember to convert this to your CDS when you plug in the numbers. Otherwise, you will get some scaling errors there, right? So, you can call this del nu, perhaps. It's V thermal divided by 1216 times 1 e minus 8. So 1.5 times 10 to the 10. 1.5 times 10 to the 10 per second. Okay? We plug this into here. That just means that we have to multiply it by this, and now you get you have gotten the hang of it, right? So I'm going to actually look up the number now. It's 2.5 times 10 to the 10 per second. Okay. No, that's the full width half maximum for the Doppler. Okay, then we want to compare this to the Lorentz. So, well, actually to the natural line broadening. The natural line broadening follows a Lorentz profile, as we have learned, and now let's, for variation, do that in frequency space. Then we know that the Lorentz profile in frequency space is 4 pi nu minus nu 0 squared plus gamma 4 pi squared d nu. So we're going to do the exact same steps. First, we looked at the maximum value. That's just where this is, right? Okay? 0. And then you can see that the maximum value involves this divided by that. So the 16 here comes up, so you get a 4, the pi's cancel, and you're ending up with a gamma in the denominator. So the max value is going to be gamma divided by 4. So half of that is going to be then gamma divided by 8. And that half, then, we're interested in where that occurs. So we just set that to delta nu squared in delta nu there, right? 4 pi squared. Okay. So, in other words, we have delta nu squared plus this squared is going to be I must have, this is of course not the correct one, because it has to be in the denominator, and the 4 has to go up. The 4 has to go up, right? That's the max value. And then you have to divide it by 2. So 2 divided by gamma. I shouldn't have skipped the algebra. I think I got it correct now. Then if you multiply this up on that side, you see that this is just gamma squared divided by 8 pi squared. So delta lambda squared is this minus that, but that's just 16, right? And this is 8, so this is 2 divided by 16, so we're left with 1/16. So this is then pi squared, or that the delta lambda is this divided by 4 pi. Okay? So that's then half width. Which means that full width half maximum for the Lorentz. It's just 2 times this, so it's lambda divided by 2 pi. Okay. Question is, how do we calculate this? Well, it was given that we were interested in the hydrogen Lyman alpha line and that we had a 2-level atom, but then we have learned that then the damping coefficient is just the Einstein A coefficient for 2, 1. Now that we can estimate in the way we did it in the lecture notes, but since that estimate is given for you there, and also you have a table which we can look into in our notes. Where is the darn table? The table is going to be somewhere around, I guess. There. Oscillator strength, nope. Einstein coefficient. L 1 to 2, 4.7 times 10 to the 8. All right. Hydrogen, Lyman, alpha. What did I say? 4.7 times 10 to the 8 per second. We have it in the same units. That's good. We have to divide this by 2 pi. So in the end, we're going to get something like 7.5 times 10 to the 7 per second. So what do we see here? Well, we see that indeed delta nu, we just call it full width, half maximum, for the Doppler line is much, much greater than the full width of half maximum for the Lorentz. The Doppler core is much more prominent than the Lorentzian wings when we have only natural line broadening. We discussed this in the course to quite some extent, that normally the natural line broadening is difficult to detect, right? And if you see the Lorentzian wings, you typically see them from the collisional line broadening component. Not always. Sometimes you can see the natural. You said that. But the normal circumstances, seldom. There are exceptions. Now, in the follow-up, they wanted us to estimate where these contributions now become equal. And then we go, okay, we have to work with the combined profile then, the Vogt function, yeah? But we want to estimate when they become equal. So then we can actually use this, what we learned in the course about that. So go again, and we see that we set up this approximation for the Vogt function, the combined, and we say that when they are equal, that is that when e to the minus x squared, where x again here now is nu minus nu 0 delta nu d, is equal to a divided by square root of pi x squared, where a is our parameter in our Vogt function that we have done. And it was the damping coefficient divided by a factor, which I don't exactly remember if it is 4 pi or not now. Can somebody look if it's 4 pi here or something else? And then delta nu d, okay? It is 4 pi. Okay, but that was good because we already calculated these quantities, right? We calculated delta nu d for the Doppler, for the situation. We calculated gamma because it was the Einstein A coefficient. So we can just plug these values in now to get our value for A. And I did that, and it was 2.5 times 10 to the minus 3. So indeed very low. Okay? As compared to the class, it's a little bit higher. And you can think about why that is, if you want. Has to do with the conditions, the temperatures that we assumed for the example. Let's see now. Okay, so we want to say when are they equal? So we want to solve this equation for x, right? So it becomes minus x squared equals to ln A divided by square root of pi x squared, right? Or if you want, x equals to minus, you can write this in a nicer form if you want, but it's not really needed. And here was the fact that we couldn't solve this fully analytically, so I had to do our little manual iteration by hand. Now, this is also done as an example because in order to get it to work, you have to understand a little bit what you're doing, in the sense that at least you have to understand where you start. Yeah? And we know that it's going to be far away from the line center in x space. Yeah? And the natural unit of x space is unity. It's nu minus nu 0 divided by delta nu d. And the natural unit, the natural broadness for the Doppler profile is delta nu d, right? So that's going to be on the order of unity. But it's going to be a little bit further away, so we're going to set the first guess to be 3. Then our second is going to be, and then we have to do this until it converges, as we said. x1 then is going to be that, which, okay, let's see what it gets. We go here, and we plug it in, right? So x1 is going to be, what do we have? So I can do this now. We're going to have x1 being negative the natural logarithm of the a value, which was 2.5 10 to the minus 3, right? And then we have divided by a square root of pi, yeah? And p square root of pi. And we had the x squared there, right? So then we set that to be 3 in this case. I should have taken an x0, of course, there, but okay. And then we have x1 to be 2.96. That's a good sign because we haven't changed that much, so we were perhaps not so bad in our first guess. Then, of course, the x2, well, you just do the same, but you plug in x1 here. Yeah? So let's do that. Let's call this x2. And we're going to plug in, instead of there, we're going to do x1 there, right? x2, 2.955. Okay. 2.955. Are we happy with that? Well, perhaps we're going to do one more and see so that we're not having some weird things going on here. But it should be fine, I mean. So we take x2 there, take x3 here, and x3 is 2.9548. So to these number of digits, it will be the same, 2.955. And we, of course, here, if you're going to be rigorous, you should define some sort of convergence, some sort of epsilon in your ith iteration, which would be, you can use the square, or you can use xi minus 1 divided by xi should be smaller than some, I don't know, 0.01. That would be converged to 1% level, or something like that. Okay? But we have now calculated that we meet them, we can call them x star, at 2.955. And of course then, the interpretation here is that for the Vogt profile in this case, we have wings and then we have a Doppler core. But actually, when these wings start to become significant, it's already up here in the Gundinum because it's at x star 2.955. So then you can see, okay, but how deep down then when they are equal does the Doppler profile go? Well, actually, of x 2.955, that is e to the minus 2.955 squared divided by square root of pi. And I mean, that's practically 0, right? So we're going to be up in the continuum. I should have done this as an emission line. It would have been more pedagogical. But anyway, we're going to be in principle at the continuum. And then we're just going to, at that point, double. We have the same contribution. But this is essentially then why it's so difficult to see the damping winds from the natural line broadening. We have to invoke normally some additional effects in order to see them. All right. Well, that was that. And let's take a break. And then we'll do, like, yeah, until 10. And